Good afternoon and welcome to this session. In this session, we will study partial differential equations. So, our course would be to understand what are partial differential equations and their classification and then their solution. First, we begin with the definition of partial differential equations, what they are. That means what they are. So, I have to go with the exact definition, then it goes with this. It's basically an equation containing one or more partial derivative of an unknown function of two or more independent variables. So it's basically an equation with one or more partial derivatives of an unknown function of two or more independent variables. What do I mean by this word partial? Okay. So of course you must have studied in your lower standard. Let's say I have a function, say f of x equal to some x squared plus 2x plus 3. Then I easily know that df over dx will be simply 2x plus 2. Okay, because it was a function of one variable, so we found total derivative. In the case there are equations which are the function of two or more variables. So let's say I have xy plus x square y square. Then I cannot directly talk about finding this. Okay, because here z is a function of two variables, x and y. So those equations which basically include partial derivatives. So here I can think of finding del z over del x. This will give me partial derivative. So here you differentiate with respect to x partially and keeping y constant. Okay. So such kind of things. And then let's say I can have also this over del y. So that will give me what? X plus simply 2x. No, 2x square y. Okay. So an equation which contains such kind of terms, del z over del x, del z over del y. Okay. This will basically come under such things. So let me give you a simple example of a differential equation. So I can have an equation like this. This example would be, say, del z over del x plus del z over del y equal to, say, x plus y. This is a partial differential equation of order 1 because here only first order derivatives are involved. First order partial derivatives are involved. I can have even this equation, del z over del x square plus del square z over del y square equals to 0. Of course, you have seen this in your calculus. I can have x square equals to, let's say, anything you write down. This does not make any difference. Let's go del y. Let me include this one even. Okay. So these equations are nothing but your partial differential equation. Okay. So our goal is now to classify them. This classification is important. So the classification of partial or differential equation. So we go for the classification. Okay. So classification, then the broader category. Okay. The broader category is linear and non-linear. The first thing would be this, linear and non-linear. And then again in linear, they are classified into different forms. That's they are called as quasi-linear, semi-linear. Okay. So such things we will now see. But before that, I want to introduce one simple notation here, okay, which I'll be using throughout my class. Okay, so standard notation. most of the time people feel difficulty to write such big things. There is this one and all these things. Okay, they do not want to write, so for simplicity they have introduced simple notations for it, and they are standard. Okay, you may read any book, you will find out these notations are not varying over alphabets. So you will get denoting P, del Z over del X is denoted by P, and Q is for del Z over del Y, and then R comes for second order derivative of Z with respect to X. Okay, and then S is there, which is the mixed partial derivative, and that is your del X over del Y, and then you have T, and this is your del square C over del T. Okay. So this is the standard notation, and it will be followed throughout. Okay. So now we go for the classification. Okay. So what are linear equations? So linear equations first. When do I say a PD is linear? Okay, that is, when do I say a PD is linear? Okay, so all I need to just check, that is, I'll write down in simple terms. It should be linear in P, Q, and Z. Okay. It should be linear in P, Q, and Z, and is of the form this is into small p. See, there is difference between this capital P and the small p. Okay, which you need to take care of. This p represent, or else let me remove the ambiguity. It's written like this: del Z over del X plus function of Q X Y Z del Z over del Y equals some r of X Y, then your standard Z plus some S of X Y. Okay. So now in short notation, they are basically written like this in short notation. I can write down this way. So this is capital P, and this is small p, plus this is capital Q, small q, equals this R Z plus some S. Okay, but P and Q can be functions of X, Y, and Z, but R strictly has to be a function of X and Y. Okay, and see, there are no power over this P, Q, and Z, so you have to take care of that. It should be linear in P, Q, and Z. So I just denote a different color to use. It should be linear in P, Q, and Z. Then the PD is said to be linear. Okay. So now let me write down an example to understand when the PD is linear. So you can have this y x square p plus say x y square or x square y square q. Write down anything, doesn't matter, because it should be linear in PQ. Okay, equal to say x square y z and plus some x or y. Okay, does not matter. Now, if you notice, then see, it is linear in P, linear in Q, and linear in Z. Nowhere I have written such kind of things. Okay, this will be non-linear basically. Okay, so just remember, for linear PD, it should be linear in P, Q, and Z. Okay. So this is the first one, and then comes second. It is called semi-linear. Okay. So semi-linear. What are semi-linear equations? Okay, again same thing. It should be linear in P and Q. Well, Z is optional, not necessarily in Z. This one is optional. So that means what? It should be linear in P and Q. Okay, and not necessarily in Z. And there is one more condition. This and is of the form. This form is very important, and please take care of the form. Earlier, this or capital P was a function of x, y, and z all, but here in semi-linear, it should be a function of strictly x and y only. It should be They are only functions of x and y. That's the basic difference between semi-linear and linear. Okay. So if a function is linear, it is automatically semi-linear. And this will be equal to your standard one, r of x, y, z. And since there is no restriction over z, so I'm not writing it. Okay. Now, let's take an example here. So let's say I have this x, y, p plus y square x cube equal to x square, y square, and z square. This is basically semi-linear. Okay. If someone asks me why it is semi-linear, so it is simply it is linear in p and q, but it is not linear in z. No problem at all. Even if it is linear in z, there is no issue. But here this is a function of x and y only, so it will be basically semi-linear. Okay. And the moment I write one more, if I write here z, it immediately becomes linear. Okay. And I remove this z and I just make it square. Now it lost its linearity. It becomes semi-linear because it is not linear in z. Okay. So the linearity of z is not important in semi-linear. That's the basic difference between linear and semi-linear. And now here comes quasi-linear, third one. It's called it quasi-linear. What is quasi-linear? So quasi-linear is it should be linear in P and Q. Again, not necessarily in Z. There is no criteria for this. Also, P is a function of x, y, z, and Q is also a function of x, y, z. Okay. Here, see, semi-linear is more similar to quasi-linear. Only the difference between semi-linear and quasi-linear is here in semi-linear, this P is a function of x and y only, but here in quasi-linear, P and Q are functions of x, y, and z. Okay. So its form would be this P of x, y, z, and I'll write down here P plus capital Q of x, y, z, and I'll write down Q equal to power of x, y, z. Okay, so this will be my quasi-linear. So let's take a simple example to understand this. I can have this x square z p plus y square z square q equal to x square y square z square plus x y anything. Okay, this will be basically like quasi-linear. Oh, quasi-linear, yeah. Okay, so this is third type. Now the fourth one is nonlinear. So it's basically an equation which does not belong to above three categories. So the equation which does not belong to above three category will automatically get placed in nonlinear. Will get placed in nonlinear. Okay. So the example would be, you can take this one, p square plus q square equals, let's take z square, or p square plus q, x square p square q equal to z x square, or you can take p plus x square y square z square q equal to x. Such equations are nonlinear, okay, because they are not linear in p or q or z. Okay, so these are nonlinear ones. So I hope you are thorough with the classification again. Okay, what we did here, we begin with the definition of partial differential equation. We found how they are formed, then we classified them into linear, semi-linear, quasi-linear, and then nonlinear. Now, the first thing would be the origin of partial differential equation. So the origin of partial differential equation. So here, what do I mean by this? That means it's a derivation of partial differential equation by eliminating arbitrary constants and sometimes even we remove arbitrary functions, okay, all functions. So what do I mean by this? So here there will be criteria again. So let's say I have an equation which looks like of x, y, z. A and B are the constants. Okay, A and B are arbitrary constants. A and B are arbitrary constants. So let's say I have an equation, a partial differential equation of this type, and I have an equation of this type, and I have to restore the partial differential equation for this. Okay. So to do this, we have to remove this arbitrary constant. Okay, we have to eliminate it by certain by differentiating it partially or doing some mathematical calculation which are acceptable. Okay, so instead let me take one example and then I'll begin with the cases how they are deal with this. Let's have an example. Say you have z equals to ax and plus b. Okay, so these are two constants. There are two constants, eliminate arbitrary constants a and b. We need to eliminate them. So to eliminate a and b, this you have done in your +2 level. Earlier, there you used to have a differential equation, an equation, and with arbitrary constants. So you used to differentiate directly with respect to x and x to eliminate the constants, and then you restore the differential equation. Here you have two constants. Sorry, yeah, now it looks good. So z equal to axy plus b. So that's my equation, and now I'll differentiate with respect to x. And let's see what if I do ay. I'll be getting ay, and say I differentiate with respect to y and get ax. So well, I'm done with this. But what about restoring, eliminating this b? Am I getting the constant? Yes, I got one. So what if I differentiate it one more time? It will be 0. And if I differentiate with respect to y one more time, I'll get 0. Okay. So these are the partial differential equations. Okay. After removing this arbitrary constant a and b. Okay. So here there were two constants, and yeah. So just one moment. Let me discuss a case here. So the discussion would be, first, if I have del z over del x and del z over del y, because z is a function of x and y. Okay, so this z, this is my dependent variable, and this x and y are independent. Okay, so whenever you are eliminating arbitrary constant, please do write this. Okay, what is the dependent variable? Okay, dependent variable is z, independent with x and y. Independent variables are x and y. And then number of dependent variables. I'm sorry, independent. Dependent, of course, we don't need. So number of independent variables are 2. And how many constants are there? 2. Okay. So here the topic of discussion is to remove the arbitrary constants and their discussion. Whether we will get a unique PD, we will get more than one PD, or we will get a PD of higher degree. All right. So such things will be discussed here. So here we discuss case 1 first. Case 1 is number of constants. So number of arbitrary constants less than number of independent variables. independent variable. All right, number of arbitrary constants are less than number of independent variables. So in this case, we will have one or more than one PD. So number of constants are less than number of independent variables, then we can have more than one PD. Let me not write one or more. Let me write down more than one PD. Okay, because you will certainly get more than one. That is indeed. So more than one PD of order 1. Okay, this is case 1. Case 2. When number of arbitrary constants. First, we will discuss the cases, and then we will solve problems, and then I'll discuss with the help of all these things. So number of arbitrary constants are greater than number of independent variables. Okay. So number of arbitrary constants are greater than number of independent variables. Okay. So here in this case, you will get a PD such things are very rare. That's a rare case basically. So number of arbitrary constant is greater than number of independent variables. So you will basically get a PD of order usually greater than 1. Why am I saying usually? Because there is no complete proof that you will get it for greater than 1 degree only. Okay, of order greater than 1. Usually we have got. So that's why I'm saying very rare case in which you will not get. So that's the word used by standard books and reference books, usually greater than 1. And then you have case 3. Case 3 says either less than, equal than, now it will be equal. So when you have number of arbitrary constants are equal to the number of independent variables. So when these two are equal, then it's the most special case. You will get a unique PD. Unique PD is guaranteed, and that too of order 1. So unique PD of order 1. Okay, it is guaranteed. Now let's discuss cases with the help of examples. Okay. So example 1. Let's say you have z equal to say ax plus y. Okay. So write down here number of constant equal to just 1. Number of independent variable are x and y, so that is 2. So here we have got number of constants are less than number of independent variables. Okay, so number of constants are less than number of independent variables. So which case it falls? Number of constants less than number of independent variables. So we will get more than one PD of order 1. Okay, so we will get more than one PD. Let's see. Okay. That means if I eliminate this constant, so I'll get a PD. Okay, and this is not unique, means I can have more than one PD. So the solution goes like this. Here you can do any calculation, okay, whatever you like. So answer this equation with star, differentiating star with respect to x partially. So I'll be getting del c over del x would be equal to simply your a, and this will be gone. Right? See, in partial differential equation there is no constant. This is not a partial differential equation because here I have a constant. So I have to remove this. So I'll differentiate it one more time. But again, if I differentiate, I'll be getting 0, and this will disqualify the criteria of this one. order 1, because indeed we need a PD of order 1 only. Okay, so del Z over del X will be A, and now let's differentiate with respect to I and say we get something. Del Z over del Y, it will give me what, 1. Okay, so this is free of constant. Now this is my PD. Okay, this is free of constant, so it will be my PD. Now with certain modification, yes, what if I resubstitute this A into this equation? Okay, then I'll get another PD. Substitute A in star. I'll be getting Z equal to A is what? Del Z over del X, and then X plus Y. This is also PD with no constant. So this is another PD, and see all of them have order 1. Right? So this is also a PD. So we got 2 partial differential equations because number of constants were less than number of independent variables. So we got 2 PDs. Okay. Now we'll discuss some more examples so that you understand it better. Example 2 would be, let's say I have this. Say z equals to ax plus by plus cxy. Here I have number of independent variables x and y2 and number of arbitrary constant. Number of arbitrary constant. How many? ABC 3. Okay. So number of independent variables is less than number of constants this time. So which case it falls? Number of independent variables are less than number of constants. So basically we will get a PD of order greater than 1. Okay, let's verify. So number of constants are greater and number of independent variables are less. So we must expect a PD which is of order usually greater than 1. Let's see how much we succeed in doing it. So I have Z equals ax plus by plus cxy. And even again, just not one PD, you will get more than one PD again. Okay, it's not one PD. I'll say PDs. Okay, of order usually greater than 1, because we cannot expect just one PD. One PD, you will get a unique PD only when you have number of constants equal to number of independent variables. Okay, only in that case you will get a unique PD, and in the rest of the cases you won't. Okay. What if I differentiate with respect to x? I'll be getting simply a plus cy, and I'll differentiate with respect to y, and I'll be getting b plus cx. And if I differentiate it one more time, so I'll see over del x2, then I'll be getting a0 free of constant, a PD. Again differentiate with respect to y, again free of constant, again a PD. All right, and now so you have to manipulate it. Okay, anyhow. Now my goal is to restore this equation once again. So in order to do that, I'll just multiply this equation. So let's say this is my equation 1 and this is my equation 2. So I'll multiply equation 1 by, x. I need x, so I'll multiply by x. So I'll be getting x del z over del x will be equal to ax plus cxy. And similarly, I'll multiply equation 2 by y. Okay, I'll multiply equation 2 by y. So in that case, I'll be getting y del z over del y equal to by plus cxy. Now I'm just going to add them. So equation 3 and equation 4. I'll add them. So I'll say adding equation 3 and 4. 3 and 4. I'll be getting x del z over del x plus y del z over del y equal to ax plus by plus cxy plus cxy. Well, I know that this part is Z, but here I'm getting a constant C. So how do I eliminate this C? Okay. So to do that, I'll take help of this equation or this equation even. See, if I differentiate with respect to x, then this will be simply C, and I'll be getting a del square Z over del y del x. Okay, will be equal to just C. And even if you differentiate this one, you get the same thing because mixed partial derivatives are equal. Okay, so here I got C. I'll resubstitute this C into this equation, and I'll be getting x del C over del x plus y del C over del y, and this is my equation here originally. This one. Okay, I got Z from here, and instead of C, I'll write down this because I have to remove the constant. This is again a PD. Okay, so how many PDs we have got? So this is one, this is another one, two, and then this is the third one, three. So we have got three PDs, and they are all are of order two. Okay, so this was another discussion. Now we talk about the uniqueness. Okay, so unique PD. Let's consider another example for unique PD as well. I have AC plus B equals, say you have x square x and plus y. So first write down number of constants. How many? A and B. And then number of independent variables are x and y, 2. So you must expect a unique PD. Okay. So let's differentiate. So A, and then del C over del x will be equal to, this is 0. And then you have here a square, simply. Now, just keep it here. I'll differentiate this to y even. So I'll get a del C over del y equals to, this will be cancelled, this will be cancelled, this will be simply 1. Alright. So in that case, yes, I can think of, should I cancel the things, or anyhow I have to remove the constants and form a PD. That's my ultimate aim. So what can I do this here? A is a square. Can I think of dividing a? If I divide them, I'll be getting a square, basically. So this will not be good. Okay. So idea here is, just a moment. This is gone, and from here I'll be getting del C over del y equal to 1 upon a. Okay. So let's multiply now. So therefore, del C over del x into, what if I multiply them? Del C over del y. This will be what? This is a, and this is 1 upon a. So it will get cancelled. I'll be getting 1. So the PD obtained is, this is P, and this part is Q equal to 1. So this is my PD. Unique PD. No matter what you do, you will always get a unique PD. Okay? Unique means you cannot, by no other modification, you can get a PD which is other than this one. Okay, you try and see, and if you get a PD, please do tell me in the comment section. Okay. And now I hope you got the idea to eliminate constants. So we will solve few more problems for eliminating the constants. All right. So some more examples to eliminate the PD. To eliminate the constants. First example is, And please note that a and a square are the same constants, so you should not expect that a square and b square are 4 constants. Okay, so number of constants, make a practice of writing this. It will be 2. Number of independent variables are again 2, so I should expect a unique PD. Okay, unique PD. So let's begin. So I'll first differentiate with respect to x. So I'll be getting simply a, and plus this will be 0, and this, the rest of them will be 0. So I got this thing. Now differentiate with respect to y. So you get this will be 0 and then b plus 0 plus 0. Okay. So I got a and b. Instead of doing any other calculation, I'll simply substitute this into this equation. So I'll be getting z equal to a. A is my del z over del x. So x into simply del z over del x, and plus b I have del z over del y plus a square. That means del z over del x square plus b is del z over del y square. This is a PD. It's as simple as that. You can do any other modification which you need, but you will get a PD which is not, you will get a PD. If you get a PD, it will be basically same. Okay, you can't expect another PD because as per the theory, there should be only one PD, and which is unique. And uniqueness is guaranteed when you have these two equal. Okay, so I'll solve one more. So let's say I get this one. So it equals to x minus a square plus y minus b square. Okay, I get this PD and I have to solve. So simply again, number of constants are 2, and number of independent variables are again 2. Okay, so again I'll get a unique PD. See, the moment why I write this, because if I know that number of constants are greater than or less than, so I'll expect more than one PD. So I don't have to think like what will come next. In that case, I'll just go on solving, and if I get an equation which is free of constant, I'll call that equation to be a PD. But if I know it is unique, so ultimately I have to work hard. Okay, so that should be our ultimate goal. Now let's differentiate. So you get del z over del x. It will be simply 2 times x minus a, and this will be 0. And you can go over this del z over del y, and you get 2 times y minus b. Okay. So one way to think of it is I can, yeah, we got it in fact. So what if I square this first? You must have understood the goal behind squaring this, because I'll square and I'll simply add it and substitute this into this equation. So 2 square times x minus a square. So here you're free to make any move. You just have to eliminate the arbitrary constant. That is your goal. You can do whatever you love. So just take here 1.4 and write down over del x square equal to, this is my x minus a square, and similarly take here 1.4 and then take this del z over del y square equals to, say, y minus b square. Now add these two equations. So I'll simply get 1.4 will be taken common, del z over del x whole square plus del z over del y whole square will be equal to simply x minus a square plus y minus b square. Well, this is nothing but my set. So I'll take this 4 here and write down this to be p square, and I'll write down this to be q square. So this is my PD, which is free of all the constants, and it is unique. Okay, so we got it. Similarly, you can think of solving many things. So let's take one more. And once we are done with eliminating constants, I'll go for eliminating functions. For that, I have a simple rule, and you just practice that, of course you will get it. Okay. This is a constant. Okay, so A and B are the two constants. Okay. So number of constants are 2, and number of independent variables are again 2. So I'll get a unique solution. Okay. So let's differentiate first with respect to x. I'll be getting A, P, e power pt, and then it will be P times cos px. Then differentiate with respect to t first and see if I get something. So A, P, and e power pt, and then again P, and the sine px. Alright, now from here I cannot think of eliminating anything, and I'll square it. Not square it, but squaring won't help me, because e power pt will be left. So instead I'll differentiate it one more time. In this equation, I'll differentiate one more time. So I'll be getting A, B, e power pt. It will remain same. It will be p square. Then cos px will be minus sine px into p. Okay. I got this at least, and then I'll differentiate with respect to t again, just to see if I get something. So A and p, and then e power pt. A. So I will remain here. Derivative of sine is again cos. Okay. So derivative of sine is again cos px into p. So I'm again stuck here. I made a mistake here. Since we are differentiating with respect to t here, why am I differentiating it again? So e power pt, and then this p will again come here, and it will be simply sine px. Okay. Now look at this equation 1 and 2. What can I say? They are same, so I'll just add it. And once I add, the ultimate thing will become, they will become cancelled. So this is the restored PD, okay, which I've got. Okay. So I hope you got the flavor of how to eliminate arbitrary constants. Okay, and now comes our topic, eliminating arbitrary functions. Eliminating arbitrary functions. Okay, so it will be basically, you may get something like some f of, it will be again some f of x, y, z, comma, some c of x, y, z equal to some 0. Okay, or it may appear like this, some phi of u equal to some v, where u and v are functions of x, y, z. That is, when I say u, I mean this, x, y, z. When I say v, I mean v of x, y, z. Okay, so how to eliminate arbitrary functions? Okay. So to do that, we have got n number of methods, but the most easiest one is, I prefer this one. Okay, so I'll write in the algorithm to convert this, but this is the most easiest one. Let's say you have given a PD of this type, phi of u comma v. Okay, so this type you are given, then convert it into this form, phi of u comma v equal to 0. These two are same. Okay, if phi of u comma v equal to 0, or phi of u comma v, or you can even write down phi of v equal to u. These three are equivalent. Okay, so whenever you get such kind of things, okay, just solve this determinant. solve this determinant. P Q minus 1, P Q and minus 1, and here you take Ux, Uy, Uz, and here you do this Vx, Vy, and Vz equal to 0. To solve this determinant, you will get your PDE without doing anything. Okay, without doing anything. So for an example, you take this. Let's say you are given a function of x plus y plus z, comma x square plus y square plus y square minus z square equal to 0. Okay, I have to eliminate this arbitrary constant phi. That means I know that this equation you can write down in this manner. Say it is your phi of x plus y plus z. This is equal to x square plus y square minus z square. Or you can also write down phi of x square plus y square minus z square equal to x plus y plus z. Okay, these things are same. Okay, but here in our case, simply do this. Okay, the solution would be included in yellow. So u equals to x plus y plus z, and then v will be equal to x square plus y square minus z square. Simply find out ux, it will be again 1, uy is also 1, and uz is 1. Now find out vx, it will be 2x, vy will be 2y, and vz will be equal to minus 2z. Okay. Now since substitute in this equation pq minus 1, ux is right down here ux, uy, uz, vx, vy, and vz will be equal to 0. Okay. So now just substitute here pq minus 1, ux is 1, 1, 1, and vx it is 2x, and then 2y, and then you have minus 2z. Okay. This is equal to 0. Now solve this determinant, so you get p times instead minus 2z and minus 2y minus q times minus 2z minus 2x, and then minus 1 into 2y minus 2x equal to 0. Everywhere I see this 2, so I'll divide by 2. Okay. Instead, I'll divide by minus 2. So I'll be getting p times, it will be z plus y, and it will become minus q times, it will be z plus x, and this one will become plus y minus x will be equal to 0. This is the PDE which I have obtained. Okay. So solving this determinant becomes easy to eliminate any kind of arbitrary function. Okay. So this is one, and this one is left for you. So you solve this one and verify whether you get the solution. So you have to solve this equation. X plus y plus z equals to f of x square plus y square plus z square. So eliminate this arbitrary function f and restore the PDE. So I'm writing the solution. You try this one. Okay. If you succeed, good. If you don't, please do comment in please do tell me in the comment section. P of y minus z plus q of z minus x equals x plus y. Okay. Now, problem number 3. Let's say I've got two arbitrary constants of x minus 80 plus g of x plus 8. I've got the two arbitrary functions f and g. Okay. So here, when you eliminate this arbitrary function, you don't have to worry about the constant because these are arbitrary functions. So you simply do this. Differentiate first with respect to x. So it will be basically f dash of x minus 80, and derivative of x minus t will be 1, and this will be g dash of x plus 80, and again its derivative will be 1. This is called chain rule. course what I did just now, and I'll differentiate it one more time. So del square y over del x2, so it will be simply f double dash of x minus 80 and plus g double dash of x plus 80. And I'll call this equation 1. I'll differentiate with respect to t. So I'm using the same notation, f dash of x minus 80, and since I'm differentiating with respect to t, so if I differentiate it one more time, it will be minus a. Derivative of x minus 80 with respect to t will be minus a, and plus g dash of x plus 80, and then the derivative of x plus 80 again is a. And most of the people even write this, so you don't have to worry about what I have written. Some people write down like this, okay? Some of them say, if I'm writing a dash, then this dash stands for x, and this dash also represents for t. Some of them write down this, f dot. So you don't have to worry about this dot. This simply implies that you are differentiating with respect to t. Okay, nothing else. Differentiating means differentiating. Okay. Some of them write this. You don't have to worry about it strictly. Okay, and I'll differentiate one more. So to y over del t2. So it will be simply f double dash and then x minus 80, and again minus a will come, so it will be simply a square. It will be simply a square, and then plus it will be again g double dash of x plus 80 times again a square, right? And if you noticed, then can I think of taking a square common? Then I'll be getting f double dash of x minus 80 plus g double dash of x plus 80. Well, this is nothing but my equation 1, and from here I'll be getting a square times del square z over del x square. Del square y over del t2 will be this. So this is my PD. Okay, here I remove these two constants. Alright, so now I'll take one more column and then I'll call for the video. We will continue in the session 2. So this is example 3. Example 3. Example 3. Z equal to y f of x. Now this will be quite interesting to solve. Okay. If you have understood the concept, you can pause the video. You can pause the video and try on your own. So at this step, you can pause the video and try. So hope you're trying. Let's see over del x del y. I'm differentiating this thing again with respect to x, so it will be simply f dash x. Okay, it will be x, so it will be g dash y. Okay, I got this thing. Now still there is a problem. How do I go with f dash and g dash? So name it equation 1, equation 2, then equation 3. I have to remove this f dash. So from here, can I do this? Because I want to take this f dash x out. So f dash x will give me what? 1 upon y then del C over del X minus G of Y. This is what I'm getting F dash, and from 2 I'll find out G dash, and then I'll resubstitute here. That's what my goal is. And G dash Y, from here I'll be getting 1 upon X, and then del C over del Y minus F of X. Okay, so just substitute here, and you are done. So therefore, del squared C over del X del Y will be equal to 1 upon Y del Z over del X minus G of Y plus 1 upon X into del Z over del Y minus F of X. Okay. So you can now even take the LCM and say it is XY. I'm sorry. This is del X del Y. Okay. This will be equal to simply, rather than this will be getting cancelled, and I'll be getting here just X, Y is gone, and then this will be del Z over del X, and minus it will be X times G of Y. From here Y is gone, okay. So now I'm taking these two terms and take minus common and write down X G of Y plus Y F of X. Well, this seems to be very familiar. Go back. Isn't it same? Y F of X plus X G of Y, so it will be same. So my equation would be square Z over del X del Y will be equal to X Z over del X plus Y del Z over del Y minus Z. Or in short notation, you can write down like this. So in short notation, we'll be getting this is X, Y, and this is nothing but your S equal to this is XP and this is YQ and minus Z. Some people write this Z equals. This is the solution. Okay. So I hope you have followed. If you have any doubt, please do tell me in the comment section. So that's all in lecture 1. We will continue in lecture 2, and there we will solve solution of PD. Solution of PD. This will be my lecture 2. Okay. Thanks for watching. If you like, then please. If you love the content of the video, then please do like, share, and subscribe to my channel. Thank you so much.